to find the value of y, you should take delta 2 by delta. So delta 1 is minus 31 by minus 31. Cancelling, you will get the value as 1. And here also it is minus 31 by minus 31. So the value is equal to 1. If the value of the determinant is not equal to 0, then they are called as non-singular matrices. So therefore here A is a singular matrix and B is non-singular matrix. Hello everyone, a warm welcome to one and all. This is Vidhyaashram ma'am, lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In this session, we will be studying Kramer's rule, that is to solve simultaneous linear equation by the method of determinants given by the Kramer. Next, we will be studying the minus, cofactor and adjoint of a square matrix. Let's see what is this Kramer rule. Suppose we have a matrix. Let me consider this as A1, B1, C1, A2, B2, C2, A3, B3, C3, where this A1, B1, C1 are the coefficients of a linear equation of the form A1x plus B1y plus C1z is equal to D1. Similarly, A2x plus B2y plus C2z is equal to D2. And A3x, B3y, C3z is equal to D3. So these are the coefficients of the factors x, y, z. And these are all simultaneous linear equation. Now how to find the value of x, y, z by the method of determinants? One of the method used to find the value of x, y, z is Kramer's rule and also called as determinant method. How to find this? So the given equation is written in the form of a matrix A and we will find the value of the determinant. So that we will take it as delta. We will find A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is the value of the determinant which we will find. Next, we will replace any one of the column by the constants D1, D2, D3. So if you replace the constants D1, D2, D3 with the coefficients of x, D1, D2, D3, next B1, B2, B3, C1, C2, C3 and evaluate the value of the determinants. That determinant we will consider as delta 1. Next, similarly, we will take delta 2. Here we will replace the value of D1, D3 with B1, B2, B3. So therefore, here we write D1, D2, D3, C1, C2, C3. So this gives you delta 2. Similarly, delta 3 we will take. So delta 3 means you are replacing the coefficients of z with respect to d. So therefore here A1, A2, A3, B1, B2, B3, D1, D2, D3. So on solving each of these determinants, you will get a real number. So after finding the real number, to find the value of x, y, z. So you have to take x is equal to delta 1 by delta. So you will get the value of the determinant delta 1 as well as delta. If you divide delta 1 by delta, you will get the value of x. Similarly, to get y, you should find out delta 2 by delta. Similarly, to get z, you should take delta 3 by delta. Thus, by replacing the constant with the coefficients of x, y and z, you will get 3 determinants. So dividing all the 3 determinants by delta, you will get the values for x, y, z. And this method of finding or solving the linear inequalities is nothing but Kramer's rule or determinant method. So in your examination, you will be having 2 or 3 marks question from the topic Kramer's rule. So let's solve now. Solve by Kramer's rule. 3x plus 4y is equal to 7. 7x minus y is equal to 6. So first, let me take this in the form of a matrix. 3, 4, 7, minus 1. So we have to write the coefficients of x in one column, y in one column. So let me take this as delta. So delta means finding the determinant. 3 into minus 1, minus 3, minus 7 4s are 28. So the value is minus 31. Now you have a constants. Replace ones with the coefficients of x. So that will give you delta 1. Let's see what is delta 1. Instead of 3, 7, write 7 and 6. And it is same. Again, 7 into minus 1, minus 7, minus 6 4s are 24. So again, minus 31. So this is your delta 1. Next, calculate delta 2. Delta 2 is replacing the constant with coefficients of y. 3, 7, 7, 6. So 3 6 are 18, minus 7 7s are 49. Again, you will get this as minus 31. Now to find the value of x, you have to take delta 1 by delta. To find the value of y, you should take delta 2 by delta. So delta 1 is minus 31 by minus 31. Cancelling, you will get the value as 1. And here also it is minus 31 by minus 31. So the value is equal to 1. So therefore, the value of x is equal to 1 and y is equal to 1. So this is how you are going to solve the value of x and y or any simultaneous linear equation using Kramer's rule. Next question. 5x plus 7y minus 3 is equal to 0. 7x plus 5y minus 9 is equal to 0. First, let us write the equation in the form 7x plus 5y is equal to 9. Now write the coefficients of x and y in the form of a matrix and find its determinant. So that is delta. So here it becomes 25 minus 49. So 5 5s are 25 minus 49. So the value is equal to 24. Now this is your delta. So let's calculate delta 1. So delta 1 means replace the coefficients of x with 3 9. 7 5 you have. So 3 5s are 15. 9 7s are 63. So the value is equal to minus 48. Next, let's take it for delta 2. So write 5 7 as it is. Replace 7 5 with 3 9. So 45 minus 21, that is equal to 24. So for x it is delta 1 by delta and for y it is delta 2 by delta. So x is equal to minus 48 divided by minus 24. So here the value is minus 24 and y is 24 divided by minus 24. So cancelling this, you will get x is equal to 2 and y is equal to minus 1. Next one, 3x plus 2y is equal to 8. 4x minus 3y is equal to 5. So 3, 2, 4 minus 3. Let's find delta. Minus 9, minus 8, minus 17. Next find delta 1. 8, 5, 2, minus 3. So minus 24, minus 10, minus 34. Let's find delta 2. 3, 4, 8, 5, 15, 32. So that is equal to minus 17. So now we take x is equal to delta 1 by delta, y is equal to delta 2 by delta. X is delta 1 is minus 34 by minus 17, y is minus 17 by minus 17. So therefore we get x is equal to 2 and y is equal to 1. So this is the value of x and y. Next question. Solve the following by Kramer's rule. Here we have 3 cross 3 square matrix. So let's write delta is equal to 1, 1, 1. Coefficients here 2, 3, 2. Next we have 4, 9, 1. So this is our delta. So either you can expand this with the numericals or you can do it with the column or row operation. So let us expand delta. So let me expand with this row. We have 1, 1, 1. So this plus minus plus. So plus means 1 into, leave the row, leave the column. We have these 4 factor. 3 ones are 3 minus 9 twos are 18. Done. Next we have minus 1. Leave the row, leave the column. We have 2, 2, 4, 1 as a factor. 2 ones are 2 minus 8. Next plus 1. Leave the column, leave the row. These 4 factors. 2 nines are 18 minus 4 threes are 12. So on solving we get delta is equal to 3 minus 18 is minus 15. 2 minus 8 is minus 6. Minus 6 into minus 1 plus 6. Next we have 18 minus 12, that is equal to plus 6. So we get minus 15 plus 12 minus 3. So we got delta is equal to minus 3. Now let's check it for delta 1. So delta 1 is replace the coefficients of x with 7, 17, 37. So 7, 17, 37. Next we have 1, 3, 9. Next 1, 2, 1. Let us expand this again. So we have same first row 7 into 3 minus 18. Next we have minus 1 into, leave the rule, 17 ones are 17 minus 37 twos are 74. Next we have plus 1 into 17 nines are 153 minus 37 threes are 111. So on solving this, we will get the value as 6. So this is delta 1. Next, let's calculate delta 2. Delta 2 is replace coefficients of y with 7, 17, 37. X coefficient is 1, 2, 4 and y coefficient is 1, 2, 1. Again, let us expand this. This becomes 1 into 17 ones are 17 minus 37 twos are 74. Next, minus 7. Leave the column, leave the row. 2 ones are 2 minus 8. Plus 1 into 37 twos are 74 minus 17 fours are 68. So on expanding and multiplying the values, you will get the solution as minus 9. So this is our delta 2. Now let's check for delta 3. What is delta 3? Write the coefficients of x as it is 1, 2, 4. Write the coefficients of y as it is 1, 3, 9. Write the coefficients of z as constant, that is 7, 17, 37. Now let us expand. Delta 3 is equal to 1 into 37 threes are. So 111 minus 153 minus 1, leave the row, leave the column, 74 minus 68. Next we have plus 7 into 18 minus 12. So again on solving this, we get delta 3 is equal to minus 6. Now we need to find the value of x. That can be done delta 1 by delta, y as delta 2 by delta and z as delta 3 by delta. So delta 1 is 6, delta 2 is minus 9. So 6 divided by 3 minus 9 divided by 3 minus 6 divided by 3. So therefore we get x is equal to 2, y is equal to minus 3 and z is equal to minus 2. So this is how we can evaluate the value of x, y, z of any linear equations given with the help of this Kramer's rule. So next we come across the minor and cofactor of a square matrix. What do you mean by this minor and cofactor of a square matrix. Suppose, let me take a matrix A of 2 cross 2 order because it is only for a square matrix. So let me take 2, minus 1, 1, 3. This is a matrix. So we have minor for each element inside the matrix. Suppose I consider this as 2. What is the minor of this matrix? Leaving the row and column containing 2. So the element 3 is minor of 2. Similarly, if you take minus 1, leaving the row and column containing minus 1, 1 is minor of minus 1. Similarly, if you take 1, leaving the row and column, so what I can say? So minus 1 is minor of 1. Similarly, 2 is minor of 3. So like this. So the minor is nothing but, as in a square matrix, the minor of an element of the determinant obtained by deleting the row and column of the A. So if you delete the row and element of the containing element, then the remaining elements, if it is in a 2 cross 2 order, the remaining element will become the minor of the element. If it is a 3 cross 3 matrix, it becomes the determinant of the remaining element. So for example, let me take A is equal to minus 1, 2, 0, 3, minus 4, minus 2, 5, minus 3, 4. Now I need to find the minor of minus 1. So minor of minus 1. So delete the row and delete the column containing minus 1. What are the elements remaining here? Minus 4, minus 2, minus 3, 4. So the determinant of these values, that is minus 4 into 4 becomes 16. Minus 16 minus of 3 2s are 6, which is equal to minus 22. So minus 22 will be the minor of minus 1. That is, when in the case of 3 cross 3 matrix, if you delete the row and column containing the element, the minor of that element will become the determinant of the remaining elements. Suppose, let me take minus 4. I want the minor of minus 4. So what is minor of minus 4? So minor of minus 4 is delete the row and column containing minus 4. What are the elements remaining? Minus 1, 0, 5, 4. So if you take the determinant of this, minus 1 into 4 is minus 4 minus 0, that is equal to minus 4. The determinant value which you will get is called the minor of the element minus 4. In the similar way, you can find for every element inside the matrix as the minor of the particular element. If you want to take for 4, you should delete the column and row containing it, and you should take the determinant of the remaining 4 elements inside the matrix. That's what the definition of the minor factor says. That is, if A is any square matrix, then the minor of element Aij, Ij represents the place value. That is, every matrix can be written as A11, A12, A21, A22. That means first row, first column element, first row, second column element, second row, first column element, second row, second column element. That represents the place of each element. So here Ij represents the place of each element inside the matrix A. So, and whenever you want to find the minor of that element, it is always the determinant of the remaining elements obtained by deleting the row and column containing that particular element. So that is possible in case of 3 cross 3 matrix. In case of 2 cross 2 matrix, if you delete the row and column, the remaining element will be only 1, and that element is itself the minor of the given element. Next is, we have a cofactor. So cofactor of an element is given by Aij is equal to minus 1 to the power I plus j. So to remember the sign, we have the signs of the cofactors of the element inside the determinant of the third order will be like this. So whatever the minor you will get, you will be writing those minor element inside one more matrix. That matrix is called as cofactor matrix. But the elements will be having a particular sign. And what are the signs here? For the first row element, it is plus minus plus. Second row, minus plus minus. Third row, plus minus plus. And in case of the 2 cross 2 order matrix, you will write the minus in one more determinant in the form of plus minus minus plus. For example, let me take matrix A. 1, 2, 3, minus 1 is the matrix. Now, what is the minor of 1? It is minus 1. What is the minor of 2? It is 3. What is the minor of 3? It is 2. Delete the row and column containing 3. What is the minor of minus 1? It is 1. So, but you are substituting the sign along with this. That is, for this it is plus of minus 1 and here it is minus of 3 and you have to replace the sign and here it is plus. So, the new matrix obtained, that is minus 1, minus 3, minus 2, 1. This is called as cofactor matrix and it is always denoted by capital IJ. So, this is the cofactor matrix. That is writing the minors of the element of a matrix in another matrix with the sign in the form of given 3 cross 3 or 2 cross 2 matrix is nothing but a cofactor matrix. So, here I have taken an example. Let me write the cofactor of each matrix. So, let me write the cofactor matrix for a given matrix. To write the cofactors of a given matrix, we are supposed to write the minors of the element first. First, let us calculate the minor of each element. So, here we have A. So, I need to write the cofactor matrix of this one. So, I'll write this as A11, A12, A13, next A21, A22, A23, A31, A32, A33. So, 1, 1, 1, 2, 1, 3 represents the places of the elements. And here I will change the sign. So, now the cofactor of this matrix must be in the form of plus minus plus, minus plus minus and plus minus plus. So, for A11, A12, A2, it is plus minus plus. Next here again minus plus minus, plus minus plus. So, just write the signs first. Next, write the minors of every element. Now, I am taking minors of minus 1. So, that is A11 means first row, first column element. So, for minus 1, what are the cofactors? So, for minus 1, what is the minor? That is minus 4, minus 2, minus 3 and 4. This is the determinant value will become the minor of minus 1 because delete the row column containing minus 1, write the remaining value in the form of a determinant. Similarly, write the determinant for each and every single element inside the matrix. So, here let me take for 2. If you delete the row and column for 2, the remaining elements are 3, minus 2, 5, 4. So, this is the determinant. Next, for the third element, delete the row, delete the column. So, you have 3, minus 4, 5, minus 3. Let's check it for other element. 2, 1 means second row, first column element. Delete the column, delete the row. You have 2, 0, minus 3, 4 inside the determinant. Next, minus 4. Delete the column, delete the row. Minus 1, 0, 5, 4. Next, similarly for minus 2, delete the row, delete the column. We have minus 1, 2, 5, minus 3. Next 5. For 5, delete the row and column. So we have 2, 0, minus 4, minus 2. Next for minus 3, delete the column, delete the row. So we have minus 1, 0, 3, minus 2. And for the last one, we have minus 1, 2, 3, minus 4. So let us evaluate this first. Minus 4 4s are 16, minus 16, minus 3 into minus 2 becomes plus 6. So minus of minus 6. Outside we have plus, so the answer will be minus 22. Next we have outside we have minus 3 4s are 12, minus 5 into minus 2 becomes minus 10, minus of minus 10 means plus 10. So it is again 12 plus 2 is again 22, but outside we have minus, so it is minus 22. Next, 3 into 3 minus 9, minus 20. So the answer is minus 29. So for positive sign, the sign will not change. Whatever you will get as a determinant value, that is only the value. But if you have negative, the sign changes. So here we have 2 4s are 8, minus 0. Outside you have minus 8, so the value is minus 8. Next, minus 4, minus 0, so the value is minus 4. Next, both are minus, so it is 3 minus 10. Outside you have minus, 3 minus 10 is minus 7, minus 7 into minus is plus 7. Next you have 2 minus 4 minus 0, which is minus 4. Next, minus 1 minus 2 becomes again 2 minus 0. Outside you have negative, so the value is minus 2. Next, it is 4 minus 6. The value is minus 2. So if you write all these values in one more matrix, that is called as the cofactor matrix. So let's write the cofactor matrix for this. So cofactor of A R, so write down in one more matrix, was a cofactor of minus 1, it is minus 22. For 2 it is minus 22. Next, minus 29. Next, here we have minus 8, minus 4, 7. Next we have minus 4, minus 2, minus 2. Minus 4, minus 2, minus 2. So this is called the cofactor matrix of A. How you will get the cofactor? Cofactors are obtained by the minors of each element by changing the sign corresponding to its places. And the minor of each element is calculated by the determinant value. So that determinant value along with the sign outside will give you the cofactor of a matrix. Next we have adjoint of a square matrix. What is this adjoint of a square matrix? So after getting the cofactor of a matrix, if you transpose it. So for example, cofactor of a matrix, you will get it in the form of A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is the cofactor matrix. So if you transpose this matrix, that is called as the adjoint of the given matrix. So that is, if you transpose, the rows comes to columns, that is A11, A12, A13, A21, A22, A23, A31, A32, A33. The elements of rows and columns interchanges. That is called as the adjoint of the given matrix. Hence, if A is any square matrix, then its adjoint is the transpose of the matrix obtained by replacing every element of A by its cofactor and denoted by adjoint A or adj A. So for the previous example, we have written the cofactor of A. So if you take the transpose of these cofactor, so in the first row we have minus 22, minus 22, minus 29. So let us write it in terms of columns. So we have minus 22, minus 22, minus 29. Second row we will write in second column, minus 8, minus 4, 7. So minus 8, minus 4, 7. And the third row we will write it in third column, minus 4, minus 2, minus 2, minus 4, minus 2, minus 2. So this is nothing but the adjoint of a matrix A. So that is the transpose of a cofactor matrix of A is nothing but the adjoint of A. Now, for a 2 cross 2 matrix, to find the adjoint A, we have the following steps. Adjoint of a 2 cross 2 matrix. The adjoint of 2 cross 2 matrix is obtained by interchanging the elements in the leading diagonal and changing the signs of the elements in the other diagonal. For example, let me have matrix A is equal to 1, 3, minus 5, 2. So this is the matrix A. According to the rule, adjoint A. So the first rule says interchanging the elements in the leading diagonal. So you interchange the elements in the leading diagonal means principal diagonal. Interchange these elements 2, 1. The second rule says changing the sign of the elements in the other diagonal. So you are not supposed to interchange, but just change the sign. Plus 3 to minus 3, minus 5 to plus 5. So this is the adjoint A. So let's see by this method of the cofactor of a matrix. So we have a matrix A here. So cofactor matrix of A. Cofactors of A. So the sign is of cofactor matrix is plus, minus, minus, plus. So what is the minor of 1? It is 2. So it is positive 2. What is the minor of 3? It is minus 5. Minus of minus 5 is plus 5. What is the minor of minus 5? It is 3 and it should be written in the form of minus 3. What is the minor of 2? It is 1. It is plus 2. So let's take the transpose of this matrix. So adjoint A is nothing but transpose of the cofactor. So let us transpose this. It is 2, 5, minus 3, 1. So this is our adjoint A. So clearly you can see they are one and the same. Either you can find by finding the cofactors first and taking the transpose, or you can use this rule to find the adjoint of a 2 cross 2 matrix. That is, interchange the leading diagonal, change the sign of the other diagonal elements. That will give you the adjoint of 2 cross 2 matrix. But where in case of 3 cross 3 matrix, you have to find the cofactors of every element, write it in cofactor matrix, take a transpose, then only you can write the adjoint of a matrix. So we have a theorem here. Let A be a square matrix, then the sum of the products of the elements of any row or column of a determinant by the corresponding cofactor is the value of the determinant. Second one, the sum of the other products of the elements of any row of the determinant by corresponding cofactors of some other row column is 0. So let's see now. So let me write the matrix. So it is A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is a matrix, and the cofactor matrix of A, we write it in the form of capital A11, A12, A13, A21, A22, A33, A31, A32, A33. So what does the first theorem says? The product of the elements of any row of a determinant by the corresponding cofactors. So if you take the elements of the first row in the matrix, you have to take the elements in the first row as in the cofactor matrix, and you should take the product. So that is, if you multiply A11, A11, A12, A12, A13 with A13, then their sum will be always equal to the determinant value. So this is what the theorem says. Similarly, if you take A21 with A21, A22 with A22, A23 with A23. That is also equal to delta. So, or you can take in the form of a column also. Column is A11, A11, A21, A21, A31, A31. So, this is also equal to the value of delta. So, taking the elements in any row or any column and multiplying with the corresponding elements in the cofactor matrix of any row or any column, the value of the determinant will be the result. Similarly, the second one says, if you take the product of the elements of any row with other row or any column with other column, the value will become 0. So that is, if you take A11, if you take this row with this element, A11 with A21, A12 with A22, A13 with A23, then the sum will become 0. So that is the product of the elements of any row or any column of the determinant by the corresponding cofactors of some other row or some other column. If you multiply any row with any other row in the cofactor matrix or any column with any other column in the cofactor matrix, the value will become 0. If you multiply the same row with the same corresponding row in the cofactor matrix, the value will be equal to the determinant value. In all the other cases, it is 0. So this is what the theorem says, and we can verify this through with an example also. Theorem 2, if A is any square matrix, then A into adjoint A into A is equal to the determinant value into I, where I is the unit matrix. So if you multiply any matrix with the adjoint matrix or adjoint with matrix with the matrix, then the value will be always equal to the determinant into I. That is, you will get a unit matrix multiplied with the determinant value. So this is what the theorem says. Next. So note here, if A is a square matrix of order n. Order n means it may be 2 cross 2 matrix or 3 cross 3, 4 cross 4, 5 cross 5. It's a square matrix of order n. Then adjoint A into A is equal to determinant A into I. We have seen from theorem 2. So therefore, we can write the determinant of adjoint A into A as determinant of adjoint A into determinant of A, and here we can take this as determinant of A whole to the power n, because determinant is commutative. Determinant of AB can be written as determinant of A into determinant of B. Hence, we have written determinant of adjoint A into A as adjoint A into A. Now here, if you shift here, then it will comes to the denominator provided determinant of A is not equal to 0. So therefore, we have one more relation, that is determinant of a adjoint A is equal to the determinant value of A to the power n minus 1. And n is the order of the matrix. Suppose you have a 3 cross 3 matrix and the determinant value is minus 4. Then what is the determinant of the adjoint A? So using this relation, adjoint of A, the value of the determinant can be written as determinant A to the power n minus 1. Since it is a 3 cross 3 matrix, we can take it as determinant value is minus 4 whole to the power 3 minus 1, because it's a 3 cross 3 matrix. So minus 4 whole square. So that is equal to 16. So therefore, if determinant have A some value and the order of a matrix is given, then we can find the determinant value for adjoint A using this relation. So next we come across the singular and non-singular matrix. What is this singular and non-singular matrix? If the value of the determinant will become 0, it is called as singular matrix. If it is not equal to 0, then it is called as non-singular matrices. So let me take an example. Let a matrix A is equal to 3, 6, 2, 4. So let me find the determinant of A. Determinant of A means 3, 6, 2, 4. So that is 3 4s are 12 minus 6 2s are 12. So 12 minus 12 is equal to 0. So if the determinant of A is 0, we call it as a singular matrix. So therefore here A is a singular matrix. So next let me take one more example. Matrix B, 2 minus 3, 4, 4. So let me take determinant of B. So 2 4s are 8 minus 4 3s are minus 12. So that is 8 plus 12, which is equal to 20. Here determinant of B is not equal to 0. So if the value of the determinant is not equal to 0, then they are called as non-singular matrices. So therefore here A is a singular matrix and B is non-singular matrix. So today we have learned what is the cofactor, minor, adjoint of a matrix and singular and non-singular matrices. We'll take up the problems related to it in our next session. Until then, keep watching, keep learning, keep exploring. Thank you.